Hey, my name is Michael Blaine Hewling. I'm in Lab Section M06, and this is Lab 9, the Spring Energy Lab. The observation was the movement of a weight connected to a spring when released from a certain position, and the result was that when the spring is included in the system, the work of the system will go to zero, and the spring will now have a value of potential energy that is added into the system. In the video, we set the origin at the fixed point of attachment for the spring, with the positive y direction going up and the negative y direction going down. We then calibrate the scale using the stick to 0.7 meters from the point of attachment to the center of mass of the string, and then we track the center of mass once Dr. Greco lets go of the weight, such as this. As you can see, as it oscillates, the points are being tracked in both the x and y positions versus time, which you can later use this information to help solve for the periods in the x and y direction. Now coming over to VPython, we edit the code created in lab to model the new mass and spring data from the video, with an orange ball as the simulation and a blue ball as the real data. So first we need to go to visualization and graph setup, and then create the new ball, which is going to be used to show the position data from tracker, which is right here. Then we come down to our initial conditions and data and set the ball's mass at 0.402 kilograms and create the new ball position, which is at negative 0.166 in the x direction and negative 0.632 in the y, which can be obtained from your tracker data. I then start the simulation running at 0.475 seconds, which is the point at which we start gathering tracker data. After that, coming down and starting the simulation, as far as running the loop goes, is essentially the same setup that we had in lab. You don't really have to change much there. However, we do have to calculate the new energy that's going to be accounted for our spring potential, seeing as the spring is in the system and is no longer doing work, but has potential energy instead. So we do this much similar to the way that we did the gravitational potential lab. The only difference is now we're using spring potential formula instead of gravitational potential, which is 0.5 times Ks, which is your spring constant, times the stretch squared. So when you run your simulation, you also want to get graph data of the delta E, the delta K, the delta of the spring potential, and the new work of the spring. The delta E, which is changed energy, will be in red. The delta K, which is kinetic energy, will be in green. The delta spring potential will be in blue, and the work of the spring will be in yellow. And when you run the program, it looks like this. As you can see, the blue ball is moving along with the orange ball in simulation very closely, as it should be, with a slight delay, which could be caused from other forces, but the simulation is very close to the actual data. Our work of spring is 0, and our overall change in energy is very close to 0. Could be due to some small force differences. Our overall energy of kinetic is the exact opposite of the spring potential, as it should be, seeing as kinetic energy increases as potential goes down, and vice versa. What does it mean? Compare the x and y periods of oscillation. The period of x was 1.62 seconds, and y was 1.52 seconds, both of which were solved for using data from tracker. As it can be seen, these periods are very close. However, they differ slightly, most likely due to other forces acting around them, and the fact that the calculation for pendular oscillation, the x direction, is t is equal to 2 pi times the square root of length divided by gravity, and spring oscillation, y in this case, t is equal to 2 pi square roots of m over k, which is mass divided by spring constant, differ. As you can see, y doesn't have many outside forces acting on it in its equation, while x does. But choosing the spring to be the system, the total work on the system will be 0 now, because no outside forces are acting on it, which causes no change in the energy from the system, and since change in energy is equal to negative work, it satisfies the energy principle. The last part of what does it mean wants to know is, when the location of your origin changed to the center of mass's location, how does it change the physics of the system and affect the 3 types of energy graphed? It changes the physics of the system because now that the origin has changed, the forces in play have changed, and the forces that exist in the y direction increase greatly due to the new power of the spring force based on its location compared to how much it is stretched and compressed. The only real difference in the graphs is that the total amount of energy in the system is increased, so the amplitude of the graph waves increase, excluding the work of spring because it is 0 in the system, seeing as the spring is included. Now coming back over to VPython, if we change the original position of the origin to 0.7 meters, which was the length of the weight at rest, and run the program again, as you can see, there's a much larger difference in the power in the y direction, and the amplitude of the waves in the graph is much higher, excluding the total energy change in the work, because those should be close to zero. However, the kinetic energy and potential energy are much greater now in these directions than they were previously because of the new forces acting from the new position.